It turns out that this is an ancient, this kind of system is evolutionarily ancient. It goes back to bacterial biofilms. Every cell in your body has ion channels. Most cells have these electrical connections. And we can do the same kind of decoding, this kind of non-neural decoding, by looking at electrical activity. This happens to be an early frog embryo. We're visualizing the electrical patterns. And again, try to decode where is it trying to get to in anatomical morphospace. And so we developed the first molecular tools to read and write these things. So here's our use of voltage-sensitive dyes to control the bioelectric patterns within embryos, to read out what all the electric communications are. Of course, we do a lot of computational modeling and simulation to understand how they connect to the channels and pumps that produce them. Beyond reading these, the kind of basically reading the mind of this morphological collective intelligence of cells, we have the ability now to write information into that as well, as people like Tanagawa do in the brain when they incept false memories into mice. So what we can do is we can take all of the tools from neuroscience, and so this is very important. The tools of neuroscience really don't distinguish between neural and non-neural cells. They all work, the concepts, the laboratory techniques, the neurotransmitter machinery, like everything works. So what we can do is we can control the gap junctions, which cells talk to which other cells, and we can control the actual electrical states by opening and closing these ion channels. So remember, there are no magnets here, there are no fields, no waves, no radiations, no electrodes. We are using the native interface that cells use to program each other. There's this electrical interface on their surface that controls the information processing, and this is how cells hack each other's behavior during normal development. And also, by the way, how some parasites hack their hosts.